1 second.
So you're not full screen yet, Hyro?
I'm not full screen, no, but you can see my.
Yeah, we see your mouse and everything, just not.
No, I don't share the screen. There's so many things going on the screen.
Right.
I just need to. 1 second. Yeah, good. So otherwise, you double hear yourself. Okay, good. Alrighty. So very good. I think slowly people will sign in. They usually know that they all just come chime right on time, usually. So very well. Let me start the presentation here. So I'd like to welcome you all once again to the online SPICE-SPIN+X seminar series here, promoted by Spin Phenomena Interdisciplinary Center that I lead together now with Karen Evershaw, who is in Duisburg, and the Collaborative Research Center led by Kaiserslautern and Mainz, in Kaiserslautern by Martina Schliemann and Burkhard Hillebrands, and in Mainz by Matthias Chloe. This is a webinar format as usual. Please write your Q&A inside the systems, and then we will ask you afterwards to, whatever questions you have, to let me know. And as usual, please check out the different schedules. We have next week's seminars, or I think a different schedule in here. I think it should be very nice. And today's speaker, we have Jack Gartside. He's a postdoctoral research fellow in Imperial College in London, trying to connect spintronics with artificial intelligence, and particularly exploiting magnonics. So we're looking forward to all that you're going to say. So I stop sharing now, and I'll ask you to go ahead and please start sharing, and then your presentation, and we'll go from there.
Great stuff.
Great.
So how's that? Is that coming through okay?
Excellent, coming through okay, great. So,
okay, great. And you're happy for me to start?
Yeah, go ahead and start. Thank
you. Well, yeah, good afternoon, everyone. And thanks a lot for the invite. I've been in the audience for many of these talks and really enjoyed them. So it's a real honor to be able to speak and share some of my research. So I'm Jack Gartside, work in Imperial College in the Functional Magnetism Group of the Physics Department with Professor Leslie Cohen and Dr. Will Branford. And the work I'm going to share with you today revolves around a new metamaterial spin system we've recently developed, and in particular using that system and its spin wave fingerprints as it's trained through a bitexture states of vortex and macrospins to leverage those properties for a reservoir computation scheme. I'd like to just start off by stressing that this is a very much collaborative work effort, and although it's me giving the talk here today, it wouldn't be possible without my co-authors and collaborators, particularly for this talk, Killian Stenning, who led the design and implementation of the reservoir scheme, Alex Vanstone, who did a lot of the key foundational work tying the spin system microstate to the ferromagnetic resonance spectra, and Troy Dion, who did a lot of work with micromagnetic simulation, tying the spectra to the microstate. And yeah, thanks to the rest of the collaborators here. So we're working between Imperial College London, UCL, and Los Alamos National Lab. So the talk here today is going to take the structure of an introduction to artificial spin systems, one of which we've got on the right here. This is the new Vortex and macrospin system. We're going to look at the problem and then solutions to the issue of microstate control in these strongly interactive nanomagnetic spin systems. I'm going to show you this new system that we've recently developed at Imperial, engineered for Vortex-macrospin bistability in the same nanostructures. We're going to look at how we can convert in a ratchet-like fashion macrospin populations to vortex by continuously cycling magnetic field, look at the FMR signatures of those two different microstates, show how we can leverage those FMR signatures to identify long-term training in physical memory phenomena, and then look at the targeted insertion of vortices via MFM tip. And finally, we're going to wrap together a bunch of those properties in a synergistic package to demonstrate a new reservoir computation scheme. And we're going to benchmark that through waveform transformation and chaotic time series prediction tasks. So to start off with, what's an artificial spin system? So while many of you will be familiar with this, I thought we'd just start from the basics and give a little run through. So there are these materials that are found in bulk that have these quite exotic arrangements of their spin. So a classic one is minerals such as dysprosium titanate, which is known as a spin ice. So here you have these atomic scale spins in these really contorted, frustrated kind of configuration, which mimic quite closely the positioning of water and oxygen ion water ice. So you can see here at each vertex you have a mix of 2 pointing into the unit cell, 2 pointing out. And this is one of those things where you start from the microscopic, very kind of simple rules for the spin by spin arrangement. And when you extrapolate that out to the macroscopic properties of the system, you end up with some quite surprising things. So specifically here, even if you cool this down to right close to 0 degrees Kelvin, you have some residual entropy left over, just like water ice. Now, the issue with these things is while they have these fascinating properties, which we are able to image quite well, the macroscopic effects of those, so you might have like some bulk lump of this thing, and you really can measure that residual entropy. What's very difficult to do is to dive inside these bulk materials and look exactly at what spin is pointing where. And furthermore, if you want to gain some kind of control over that, so, you know, if you break this ordering rule, and that does happen in the bulk material, you end up with a spin defect that has some similarities to a magnetic monopole. Now, with a bulk thing like this, you're relying on kind of macroscopic signatures of populations of those, and you're relying them to occur somewhat stochastically. People have wanted, for as long as they were interested in these kind of materials, to be able to really dive inside with a lot more freedom. So one solution to that is using all of the benefits of nanofabrication and metamaterial engineering to be able to capture as simplistically as possible the kind of microscopic arrangements and spin frustration, and then engineer that into your simple 2D nanofabricated system in such a way that the whole array that you've nanofabricated on a silicon chip still retains those fascinating bulk properties. So we've looked at spin ice here. The classic is artificial spin ice. So we take a flat silicon chip and put down simple magnetic materials. So here we're just using permalloy, an alloy of nickel and iron. And we make each island small enough that it's a single domain ferromagnet. So looking over here, we have a magnetic microforce, a magnetic force microscope image, that's MFM, which can really show us on every single spin in this array, where are they pointing? And one of those monopole defects I mentioned, where you've broken that ordering rule at each vertex. If you look at all of these, they're following what's known as the ice rules. That's the trying to even out the number of positive and negative magnetic charges. So you're substituting that for your positions of your hydrogen and oxygen ions in actual spin ice. Sorry, actual water ice. And you can really see here that you can map all these things out. So it's really nice. You get this good analogy to these bulk minerals here, but because you're nanofabricating this thing, you don't have to worry about the intricacies of chemical synthesis. You simply have a CAD file. And if you want to divert from, you know, these sort of structures that are found in nature, like water ice, you can really design anything you want. So this is a really nice piece of work from the Leeds group back in 2018, where they took a Penrose tile and converted that into a artificial spin system. And just by changing the arrangement of these magnets, they ended up with a metamaterial that had quite astoundingly different properties from this earlier one that I showed you there. So you have these sort of systems, and a big degree in a big part of the fascination for the field, and definitely for myself, is that you have this huge range of microstates, a lot of which are more or less energetically degenerate. And that's the quite rare thing. So, you know, any system that has this many particles that you can arrange in one of two ways is going to have 2 to the n possible states. But usually there's a very strict ordering of those in energy, which means that you hardly ever see the high energy ones. However, in this kind of system, you have a really large manifold of more or less energetically degenerate states, which you can in theory, access and prepare. And from the infancy of this field, there was a lot of work saying that certain states of these would have quite astounding properties, both in a fundamental physics angle, like the monopole state we saw earlier, or some ground states, which we'll see in a few slides, and also from an applied perspective, which is what my personal research interests lean more towards. So recent directions that have taken these artificial spin systems for an applied standpoint are reconfigurable bangonics, where certain configurations may act as really efficient bandpass filters at certain frequencies, or going back to the fundamental physics side, certain microstate configurations may allow you to observe spin wave level repulsion and other associated phenomena. So this all sounds great. However, the big problem is, how do you prepare these states? So, people talked about a lot of the promise of all of these possible states, but for many years, these states weren't really being prepared experimentally. There was some great theoretical and simulation work showing that, it really does look like they have these properties. But aside from just putting on a big magnetic field and pointing them all in the same direction, not that much was happening. So people could scramble the field. So, this is, if we imagine putting a global magnetic field on here, all of your spins simply point in the same direction. That was, what a lot of the work was being done on this type of state. You can then also scramble it with a AC demagnetizing field. So you get something random, but again, you've lost control and it's very difficult to prepare the exact same state again. Or you might be able to heat the system up and thermally anneal it into its ground state. So for something like square artificial spin ice, where the ground state's quite well defined, that's possible. So this is really nice, again, from the Leeds group piece of work where they took square spin ice and showed that you could get the whole thing to slip into its ground state, which is a big result at the time. But even if you go to a slightly more complex ground state, so for instance, the Kagame system, rather than having a single vertex ground state here, so you can see each vertex has two like charges opposite, and then the vice versa in the other axis. The ground state for Kagame is much bigger and much more subtle, and this was actually too elusive to be paired by thermal annealing. So the direction of the Imperial group for a long time has been driving our efforts towards providing new microstate solutions for the field to really crack this problem open and allow spin ice and related spin systems to move forward, both in terms of the more elusive physical phenomena and, closer to my personal research interests, try to push the system towards some of the applied promise that it's had since its infancy. So one thing we've done a lot of is MFM, this technique I mentioned before, where you take basically a magnet on the end of an AFM cantilever and you can use it to image a bit like a divining rod. So, you've got a magnet, it's got its own magnetic field. Usually people try to tune this so the magnetic field's weak enough that you don't disturb the spin texture of your nanosystem. However, I thought, why not crank it up? If we use a strong enough magnet that can locally break the coercive field, we might be able to get some interesting stuff. So I took a strong magnetic tip, scanned it over just watch that video one more time. So we're simulating here in MeMax, me moving the tip over the wire. And you can see it does get strong enough to really tie the magnetization of this nanowire into a knot. So this is something like 150 nanometers wide, simulated infinitely long here, and 15 nanometers thick. So this thing that we're left with, this topologically stable knot here, is something known as a 360 domain wall. So once we saw this in simulation, we thought, great, let's try and take that to the lab. And here's some real MFM data. So this is a nanowire. We're looking just at the middle section, so we're not expecting to see any of the end charges that MFM is usually sensitive to. You'll see a slight ripple here where some of the topography is leaking through. I then took a much stronger MFM tip. So you can see this black contrast here is what was telling us at the time that the tip was strong enough to put these distortions of the magnetization in. I then retracted the tip where I've marked with this pyramid here and came back with a low moment tip and imaged again. We were able to see these really strong light and dark regions here, which are the magnetic force microscope signature of that knot, kind of the same knot that's forming here that was in that video. So something we noticed is where you saw in that video, this knot doesn't get put in. So it's not known in the field as a 360 domain wall. It's not put in static. The two separate domain walls that form it, so you have a 181 and 181 on the left, and another 181 on the right, hence the term 360. They are formed with some inertia, some stored potential energy, which rapidly converts to a kinetic energy, separating them. So an infinitely long wire, they simply come back together and you're left with the sort of thing we see here. But we thought if we could shrink the wires such that this initial inertia that they form with, so basically you have you're using the exchange interaction a bit like the spring on a pinball machine. So they form in such a contorted state. You can see here that as they straighten out, they separate quite violently. And when the wire gets short enough, they separate so hard that the domain walls hit either end, unwind, and you're left with a nanowire magnetized opposite to what you started with. And this starts to look really like something that would be useful for writing intricate microstates into these dense arrays. So we took it again to the lab, and so you have to bear with me, I've got a bit of a cold. And we took a range of nanowires magnetized in one way. I've got a schematic here showing they're all magnetized down the page. We came with that strong tip that we showed before, scanned over where the dotted line is, and imaged again. And you can see from the MFM image that the ordering of the poles has been reversed just for the wires that we crossed. So you can see in the schematic there that basically those magnets have been flipped. So this looks great. We're still in a relatively easy system here where we've separated the nanomagnets so they're not really interacting. We wanted to know, can we take it into one of our dense, strongly interacting artificial spin systems, our SPIN-ICEs? So you can see here as well, we came in with a bit more care and tried to write this sort of, if you will, artificial antiferromagnetic state. So moving that into SPIN-ICE, we talked about this interesting state, one of them being where you could kind of break the natural low energy ordering and put these like charges together. So we were able to come in and flip that one single bar with the tip. We were able also to do these more collective excitations where we could put in whole chains of these things. And this was in a paper published in Nature Nanotechnology in 2018, demonstrating this technique. So again, I mentioned states that weren't, something like the ground state, which you think should be the easiest state to access. Counterintuitively, in these systems, the ground state is subtly lower in energy than some of the energetically adjacent states on the manifold. So particularly the Kagame one, which had resisted attempts to prepare it via thermal annealing. This is the smallest system which can host the Kagame ground state. So it's prepared by, if you imagine taking all of those magnets and selectively reversing half the magnets in this quite intricate pattern, what you end up doing is creating alternating chiral loops throughout your hexagons, which close each other's flux and lower the total energy of the system. So you can see it's this big complex thing. And we were actually able, with our tip-based technique, to prepare this state on the left, write all of the bars that I've colored in blue, one by one of the tip, and end up preparing this state that had otherwise eluded experimental observation. So it's a nice early result for our microstate control efforts. And it works really well if there's a certain state that you want to prepare in the lab, perhaps as a proof of concept, or you're looking at more kind of fundamental physical things where just preparing one tiny thing of it is enough for what you want to do. However, if we're trying to extrapolate out to more functional or device-based systems, it's not quite big enough or fast enough to do anything useful. Also, it's running off this big mechanical cantilever, which is really unsuitable for any type of embedded application. So what we were thinking is there some middle ground between this kind of total spin by spin accuracy microstate control and the more coarse techniques that were available in the field that I mentioned before, where you just slap a big magnetic field on? So we were thinking, kind of waiting for a vacuum to pump down one day in the lab. I think it was actually on the back of an envelope, I drew this system where you would modify the coercive field. If you could find a way to do that, of alternating rows of your system, still just using a big simple magnetic field, you'd be able to drive the system through all four. So this is this square artificial spin-X system. All four of its what you could call pure microstates, in that every single vertex has the same magnetic charge profile. And this is actually enough to do that. So the trick is that the first two states you can do by putting the field along the y-axis. The second two you can do by putting the field along the x-axis. So you either have an XY magnet or you rotate your sample. But that small modification is enough to do that. And the reason that we were interested in this is there's been a growing direction of using artificial spin-X as a host system for reconfigurable magnonics. So magnonics is, or kind of spin wave engineering, is taking advantage of this type of system so that the shape anisotropy you get from cutting them up effectively provides their own bias field. So you get nice spin wave resonances without having to stick a field on. And because you are also getting local dipolar field coming out of these things, the mode frequency is really sensitive to what that local field is doing. So you can make the neighboring bars, by changing their orientation, i.e. by changing the microstate, you can gain a lot of control over the spin wave spectra. And again, there's been some really nice work done on this, but where for us it was hitting a bit of a wall is, the big promise is the different dipolar field landscapes and the fingerprints they impart on the spin wave spectra, but without a means to drive your system through different microstates, the range of spectra you can access is also really limited. So we took our system and it kind of sits on a coplanar waveguide like this. And as we drive it through these different microstates, you can see that the spin wave spectra radically changes. So this was done in a recent paper in Nature Communications, which came out earlier this year. And I just want to stress here that this tying of the microstate to the spectra was driven in large part by our PhD student, Alex Vanstone, and a postdoc in our group, Troy Dion, was instrumental in doing the connecting simulations between the microstate and the spectrum, also based on some earlier work by Dana Rue in our group. So this came off really nice. And as well as you can imagine from a kind of purely functional, a lot of our communications are done in the microwave region, and you can see moving between these things, even at the zero field point, you can have 3 modes active here, 2 here, and you kind of have 4 here, 2 are lower amplitude. But you're able to activate, deactivate, and also with small amounts of magnetic field, tune quite strongly the frequencies that your modes are active in. So you're getting a lot of reconfigurability here from a very small modification to your array, that changing of the width of every other line of bars. So we were quite encouraged by this. And then we thought, still wanting to use global field, how much further can we take this? So
hang on, I'm having some difficulties with sound. Jack, are you there?
Okay, can you hear me? Yeah.
Yeah, I think it was just for a couple of minutes.
Okay.
Yeah, like the last 30 seconds, maybe you can come back to that. Okay,
great. Yeah, so people had predicted for a while that you should be able to prepare these sort of systems that Troy Dion did in our group, where he had the idea that if you could break the symmetry of your magnetic charge ordering at the vertex, So one of those states we showed, this type 3 microstate, you can see that you have this highly asymmetric ordering. That should give you the conditions that
yeah, we're having difficulties, Jack.
You have at a point in phase and out of the
Jack?
phase branch. Are you losing again?
Yeah, I think we're having difficulties with the internet connection, not been very stable from maybe from your side. I'm checking with others.
Yeah, no. Okay, so let's just see. I'm going to try to change Wi-Fi network and see if that gives us anything better.
I mean, usually it's best to be connected to a line, so otherwise it's difficult.
Yeah, how's that?
Okay, let's give it a try.
Yeah.
Go ahead, continue.
Okay, so yeah, so just skipping through. So we were able to use the microstate control techniques to prepare this type 3 state that had the prerequisite breaking of symmetry in the magnetic ordering in the microstate to create these points that are labeled 2 and 5 here, where you have an in phase and out of phase oscillations coupled in adjacent nanomagnets. That gives you level repulsion between your spin wave modes. So we've got a simulation on the right here, and then in different samples and different measurement orientations, we've measured these level repulsions experimentally. So again, we were interested in how much further could you take the degree of microstate control that was possible still using a global field. So something we were wondering is, you have everything typically in these systems is done using macrospins. And a PhD student, Killian Stenning, in our group was interested in simulation, in finding systems that were bistable between vortex and macrospin. So we had an ACS nano simulation paper on this in 2020, and we wanted to try to combine this with the system I've just shown you. So again, here's an SEM image of the array, and here is a spin wave spectra, FMR, taken differential mode at 0 magnetic field. So you get one peak here for the wide bars in a macrospin mode, and a higher frequency peak here coming from the thin bars. Here's an image of the magnetization state, simulated MFM image, and real MFM corresponding to that state. And then what we decided to do was use a minor field loop that was a field magnitude that was strong enough to reverse these wide bars, but leave the thin bars stable. And we looped 30 times through that loop and took another spectra. So we were expecting to see something different. It shocked us quite how different it was. So you see that the wide bar macrospin mode is really effectively gone, and a new mode has emerged at lower frequency. So we weren't sure at first whether we had just demagnetized the sample or some kind of AC demagnetization, or something else was going on. We'd hoped we were going to prepare vortices, but we were unsure. So we took an MFM image, and you see here this new states that look radically different from what I showed you up here have emerged. So we thought they could be vortices, but just to check, we did mu-max3 simulations and projected those into simulated MFM images, and you get this kind of checkerboard pattern, which matches really nicely what we were seeing under MFM. So it looks like this field looping back and forth was indeed creating vortices. And just to show you how different those spectra were again, the blue is the initial spectra saturated at -200 millitesla, and then in red, this is after 30 training loops at 18 millitesla. So we did some micromagnetic simulation of the energy of the two states. So we prepared the bars in a vortex and a macrospin state and looked at the difference in energy. And we found that there's this bistable line that you can hit, which allows you to use this trick to loop the system back and forward. And every time you go through one of these loops, some subset of your population will convert from a macrospin to a vortex. So the system we're going to consider here is 600 nanometers long and 200 wide. Every point on this is using a 25 nanometer thickness, and it's permalloy. So again, here's the MFM image corresponding to the blue state. you see everything's in a macrospin state. And then after looping through all of these, you get these chains of vortices. So it's quite interesting seeing how they're coming in together, kind of collective behavior. So looking at how these form in a micromagnetic picture, going from this saturated to this vortex state, we did dynamic simulations. So we took a saturated state here and then watched over a couple nanosecond timescale as the topological end charges are drawn together where they combine into a vortex core, which then remains stable in the center of the bar. So that's the kind of detailed micromagnetic picture of this vortex formation process. So we wanted to understand how this was happening and also how those collective sets of vortices were forming. Because a vortex, the shape of the magnetization, the way it's wrapped around there, means that essentially relatively no dipolar field is leaking out of that, very, very low compared to the macrospin where you get a lot of leakage. So the fact that we were seeing this collective behavior surprised us. We wanted to investigate how that arose. So what we're doing here is from the negative and positive legs of each loop, we took an image afterwards and start with everything's a macrospin. As we loop, at first you see that you get this stochastic nucleation of well-separated individual vortices. Then on successive loops, we find that the number of vortices that nucleates each loop both increases, and also that you're far, far more likely to have your vortex, a new vortex nucleating adjacent to an existing vortex. So there really is this new collective property emerging from the fact that we've designed this system to be bistable in energy between vortex and macrospin. And as you continue to loop through, these chains grow, and you're seeing that you're starting to get these domains emerging. So the domain structure is relatively loosely defined here at the full loop stage, but you'll see as we progress to higher numbers of loops, you end up with these quite well separated. So, particularly here at 30 loops, you can see your macrospins are all well clustered together. So you have this, totally new type of domain formation being engineered in at the metamaterial design stage. And as we were doing this, we took spin wave FMR heat maps after 0, 30, 0, 3, 10, and 30 loops. And what you can see here is something really striking. So at first you get this faint hint of a new set of modes, which gets stronger and stronger. And at 30, you see these really striking spin wave modes with this highly nonlinear curvature, and also this kind of textured checkerboard pattern higher order modes coming in up here. So it's this really nice thing where usually with reconfigurable magnetic crystals, the switching between mode profiles is something quite binary. You tend to be in one state or another, or a handful of them. But this gradual emergence in amplitude is something that's relatively rare. So comparing with some of Troy's simulations, you see that we reproduce these highly curved X-shaped modes, and also this kind of textured checkerboard-like behavior up here. So looking at what is causing that curvature, which again is quite rare, typically the spin wave modes that you see in these reconfigurable magnetic crystals are these straight Cattell-like modes. What's happening is the vortex core is relatively free to move. So, even while you're in a vortex state, applying a positive or a negative field will displace the core. And the M1B and M1A modes you have here are the excitation above and below, respectively, that core. So you can view the size of this region a bit like the, let's have one here, the volume of air in a bottle. So as you're effectively moving the liquid level up and down as you shift that core left and right, you're able to tune that frequency. So having that degree of nonlinearity with relatively small field shifts offers a lot of reconfigurability for the mode profiles here, specifically particularly when you're combining it with the Cattell-like modes as well. So where I showed you the MFM pictures going step by step, we also decided to do that with the FMR spectra. So what we have here is spectra taken at a constant bias field. We just use -1 millitesla. Remnants works too, but you get slightly better signal to noise here. And we go from a totally macrospin saturated state in dark blue, all the way to a highly vortex state in red after 30 loops. And you get this waterfall-like behavior, where not only is the amplitude smoothly decreasing, it's quite rare in these systems, as I mentioned, you're getting these really subtle shifts in the mode frequency. If we look over at what's happening to the thin bar, even though none of those are reversing, you're getting that same subtle decrease. And this is all because every time you convert a macrospin to a vortex, you are altering the dipolar field landscape, which, as you know, Alex Van Stone's work has shown, there's a really nice preprint on the archive at the moment. Your mode frequency is really sensitive to that. And that shows up really nicely here. So we were really happy with the work to this point. And something I want to show here is, I want to explain why we've got the thin bars in this system. So what we'd hoped is, you know, as we showed before, you're getting the system's very sensitive to the dipolar field landscape. And that's actually what was increasing the likelihood that your vortices would nucleate adjacent to other vortices. So you can really change the likelihood and the rate of the vortex formation by what your dipolar field landscape looks like. So having these thin bars, which we never switch and which always remain as a macrospin, gives us a built-in intrinsic bias field, which we can reconfigure to redirect that vortex formation process. So the only difference between these three curves, so just to talk you through them, we've got the purple, blue, and green curves represent the macrospin amplitude. And we're going through a training sequence here. The orange, red, and brown curves are the vortex amplitude. And you can take the mode amplitude as directly proportional to the population. So we've done the analysis tying that amplitude to the MFM images, and the two are very nicely linked. So the difference here, looking at the number of vortices, so we're starting from an all macrospin state in each case. In the orange case, the thin bars are set up so that the system is in its ground state, that type 1 state I showed before. And what you can see here is you get a very slow, relatively gradual increase in the number of vortices. However, at the end, after 30 loops, you have significantly more vortices than other states. Now, the brown state is where we prepare the system such that every vertex is in the most energetically unfavorable state. So everything's in this monopole defect state. And what you can see is you get a very rapid increase, big jump for your first loop, and it stays high. But by the end, you end up with a substantially reduced vortex population. So what's going on there is, even though this high field at the beginning is creating a lot of these vortices, because everything's so energetically unfavorable, you're getting locked in these little kind of minima pockets where the system isn't able to fully reach that high vortex state. And you get the corresponding, you've got the kind of inverse relationship with these numbers of macrospins. So the blue curve shows what happens if you set the thin bars up such that the system's in its ground state. Increase right down to much lower at the end, and then this purple thing that stays high is when we're starting off in the highest energy state. So those thin bars give us a massive amount of control over the training dynamics here. And everything we've looked at so far has been changing the macrospins into a vortex. Now, it's a reversible process, but crucially, the switching fields are well separated. And when I mentioned a ratchet-like effect, what I meant is that the difference in these coercive fields, so for a macrospin to flip, it's at something like 16 or 17 millitesla. Now for a vortex to flip back to a macrospin, you're up between 24 and 27 millitesla, depending on what your thin bars are doing. So you have this whole window around here where you can loop the field back and forward. And while every time your macrospins flip, there's a chance that some of them will become vortex. So it's between 1% and 3% of your macrospins will turn to a vortex every time you flip them. You're never getting rid of any vortices because they're at a much higher field. So that ratchet effect means we can drive back and forward here all we want, and you'll be constantly increasing the share of vortices in your system. So you can see here, we can take the system, increase the field. We have the number of vortices left in these lower three lines, and you can see it gradually drops off. And the same, the number of max spins gradually increases here. So you get these kind of nice sigmoid-like non-linear changes in population as you ramp the field up. So we've shown a lot of control, all using global field processes where you have this initially stochastic and then domain-like formation. So that kind of tied into our original question: how far can you take a global field-based microstate control system in one of these artificial spin metamaterials? Now, tying this back to our earlier work, really zooming into the microscopic level and seeing how much can you do on a spin-by-spin basis with a tip, we wanted to integrate that with this artificial spin vortex system. So what I've got here is a all max spin system that I then come in with my same tip writing technique I mentioned earlier. And we've modified it here so that when we write the tip, we're not reversing max spins, we're actually injecting vortex cores into these bars. So between this image and this one, what I've done is come and hit these 6 bars with the high moment tip. So really nice, you get vortices there, nothing else has changed, great. We then decided to come in and put another line of vortices up here. Now the reason will become clear in a second. So what we wanted to do is see if we could use this system to bridge the gap between our tip-based single spin rating and a global field looping where you can get more stochastic evolution of the intrinsic dynamics and memory phenomena in your system. So here's our prepared state. And what we're going to do now is loop the field back and forth. However, where previously we were looping a field such that all the max spins were switching, here we're using a substantially lower field. So I mentioned earlier, the coercive field for the max spins is about 16, 17 millitesla. Here we decided to loop at 13, so nothing should happen, right? But what ends up happening is adjacent to these chains of tip-written vortices, your global field is still driving microstate control. It's really nice. So nothing else has changed, but on the end of this chain here, we are putting in a series of type 1 vertices. So type 1 you can recognize by this nice checkerboard pattern at each vertex. Nothing else has changed. We come back then with a second loop, and between these two lines, we've kind of created this corridor here where the dipolar field landscape has been modified by the vortices, which has also really changed the coercivity. You get that type 1 line spreading right between them. So that, this is early work here, and we're going to flesh this out a lot more, but it's really shown us that we can combine this tip writing technique to seed global field driven dynamics. And what we can then do as well is we decided to run just a half field loop. So just back to just the positive half, and we can actually, if you like, heal this line of type 1 vertices that we put in and go back to the tip written state. So going again to, so we looked at some training earlier, and we wanted to see what could we do that was a bit more complicated. So we showed this ratchet-like thing that I mentioned, where we're constantly driving up the number of vortices. Now, we're interested in taking this to some form of, where you can input some sequence of data and your system would start to respond to it in an interesting way. And, your data is, if you imagine the field loop where you're going to create more vortex as a 0 very crudely, we'd effectively just been putting in long series of many zeros. And we wanted to see what happens if you start putting in some ones. So if you take a 0 as a field, that's going to take some subset of your max spins and turn them to a vortex. We want to see what happens if you go the other way. Obviously not totally saturating, so you're still remaining memory. You have some max spins, some vortices, but combining them so you're increasing a bit each way. So what we've done here, it's a little bit of a subtle plot. So give a moment to explain it. And this -1 point of the field loop represents 6 different states, 6 different different initial microstates. And the difference between them is how many of these vortex creating training loops have been performed on them. So all 6 of these curves started off in all macrospin state. The blue one, we did 0 loops, we didn't do anything else to it. So that stayed everything as a macrospin. And the y-axis here is the macrospin peak amplitude, basically how many macrospins are in your system, what fraction. So this blue point here is when 100% of your bars are in the macrospin state. Then we put 2 training loops. You can see that the number of macrospin drops off increasingly as we do more and more training loops, right down to 30 at the bottom. What we then did at point 0 is applied a field that was chosen to convert roughly 50% of the vortices back to macrospins. So you can see that these jump up. However, it's still really easy to tell which of these states had more vortices previously. So everything's had the same stimulus done to it, but they've all retained their history really nicely. So that's a good initial test of some kind of memory capability. However, it's quite basic. So what we then decided to do is how long does it retain that memory? So from field loops 1 to 15, we were cycling back at that 16 millitesla again and again over those 16 loops to put more vortices back in. So we've been calling them recovery loops. You can just imagine them as you're kind of rebuilding that vortex population. And what you can see is that definitely for the first 5 or 6 of these recovery loops, it's still very easy to work out which system had been more well-trained in the past. So not just are the amplitudes different, but if you fit exponential decay functions to each of these, you can find that your alpha, so you've got your e to the negative alpha t, where t is the number of field loops. Your alpha, this decay constant here on the y-axis, is a really nicely trackable function of how many training loops you'd had done prior to this stimulus. So not just the number of vortices and macrospins retains training history, but actually the dynamics, the rate that they change at. So importantly here, and somewhat subtly, it'll hopefully become clearer later on, while they start well separated, the separation gradually decreases. So you're taking these different initial states and the system is converging from them towards a common state while it's driven through long input sequences. And this property is often termed as an echo state property. And it's one of the big boxes that you need to tick to have a system that looks good for reservoir computation. So taking this a little further, what we decided to do is look at how much that stimulus field matters. So at 0 here, we hit everything with 21.5. What we've done here is taken a single state and driven it through a much longer training process where, so what these numbers mean is this point here, we hit it with 21 millitesla. So you're turning some handful of your vortices back to a max spin. And then we do 2 of these recovery loops afterwards. So what this region means is we do 21, 16, 16, 21, 16, 16. And what you can see is here, the recovery loops are putting in more vortices than your 21 millitesla stimulus fields are removing. But as you increase that even by half a millitesla, you reach this point where you're kind of at an equilibrium. You're putting in and removing the same amount of vortices each time. Then you jump up even, we're looking at halves of a millitesla each time, and you start to really change not just that gradient, but this big jump in between. So, you can change your applied field by half a millitesla, and this system, once it's been trained, is really sensitive to that. So you have these small linear increases here, big non-linear response, both in gradient and in initial jump response. So as we're going through these tests, the thing that's in the back of our mind is this type of machine learning called reservoir computation. So the type of machine learning that most of us are familiar with and kind of grabs most of the headlines these days is something called a deep neural network. So it looks something like this. You have a bunch of inputs, goes through this big interconnected matrix of weights. every single one of which you're training, updating, spending time and energy on. And then it gives you your output, which is typically some type of prediction, classification. And these things are immensely powerful. And all of the wild results we've seen in recent years from Google DeepMind and the like and OpenAI are typically done through this type of system. However, they're radically computationally expensive, not just in your processor time, how many coffees you need to go before your model is trained. These things are getting so big and so globally used that their energy footprint is spiraling out of control. And at the moment, it's already as much as the whole country of Argentina uses. Some of you may have heard of a natural language processing model, GPT-3, created by OpenAI. To train that took, I think, 4 gigawatt hours. So it's the total energy output of 3 nuclear power plants running concurrently for an hour. That's one model. And shockingly, there was a recent white paper by OpenAI that we have this new analogy to Moore's law, where the energy cost of global machine learning doubles every 3.5 months. And that's since 2019. There's been a recent update that shows this trend is continuing. Some say it's accelerating, some say it's about the same, but it's still radically unsustainable. So the idea of reservoir computing is you have your inputs, but then you're replacing this deep neural network of all of these hidden layers that you're updating every step with this bunch of strongly interacting hidden connections, which you're not training on. Instead, what you're doing is defining a few output points that you can run simple linear training on. Now, the reason this works is you have this strongly interacting nonlinear connections in here, which can project a very high dimensional problem on a low dimensional space. So you effectively are able to do a linear training problem on a non-linear task. And this radically reduces both your computation time and, more critically, for what I'm interested in personally, your energy footprint. So, for us to hit any type of zero carbon future, we need something that's going to cancel out this massively unsustainable doubling of energy cost. So we're only training this small number of outputs, and it's not great for everything. It's definitely not going to totally replace deep neural networks. They're still the most powerful. But what its strengths are is in temporal data series and the prediction, transformation, and classification of those series. So you can imagine already we're starting to move towards dedicated AI or neuromorphic processors in things like our phones, or even we're getting towards it in Internet of Things devices. But most of those are really simple tasks, something like saying, okay, Siri, and having to pass that bit of voice recognition. But if millions of people are doing that worldwide, if we can make any type of a dent in the energy footprint of that, we're really helping the global energy consumption. So reservoir computing, this reservoir that I described in here fits a lot of the same parameters as some of the physical systems that we're interested in. So Karian Evershaw-Sitter gave a fantastic talk recently on using a skyrmion-based system for this. As we were going through classifying and looking at this ASVI system, we realized that it ticked a lot of the same boxes. So prerequisites for good reservoir, you need a wide range of distinguishable states. We've showed that going between our vortices and macrospins, we have that. There's a huge microstate space, and you can quite easily discern them, especially for how different their spin wave spectra look. You need a really non-linear response to a linearly increasing input. We've shown that from a few points here, this kind of small changes in training field, and also the populations following the sigmoidal curves up here. You need strong inter-element coupling. We've demonstrated through the vortex writing how significant a difference putting in these vortices can make to the rest of the array. And you also need both a short-term memory of what's gone on before. So we've showed you that here with how well separated these different curves are, where the only difference in them is what the initial state was. And you also need the ability for them to gradually forget those differences, so you don't just get locked in these forever separated trajectories. And again, we see that with these systems tending towards each other. So as we're ticking all these boxes, we think it's probably time to try to implement some kind of reservoir scheme. So giving credit where credit's due, our PhD student, Killian Stenning, has done an amazing job leading and implementing our reservoir computation scheme here. So yeah, all credit to Killian. So the scheme basically goes where we take a input data set, convert it to a series of magnetic fields. So you imagine a 1 in your data set is a high field, a 0 is a lower one. And we successively subject them to our system. It changes state each time. And after each time step, we measure the FMR spectra at remnants. And we've seen that the FMR spectra really changes based on these microstates. We then take each frequency bin of our FMR spectra, so there's 300 of which, and this is how we're achieving that projection of a huge amount of connections onto a small amount of trainable outputs. There's billions of these magnets. You can't image each one in any kind of reasonably fast or cheap way. But we have 300 of these bins, which is a reasonable amount of outputs to train on. We then train on those, and that allows us to produce high quality predictions. So looking at some tasks that we've run the system through, we thought a great place to start is waveform transformation. So you take an input data set. We started with a sine wave. So you're showing your system a series of magnetic fields that are sinusoidally increasing and decreasing. You then are training on the FMR outputs of that field series, and you're training them to transform to some y of t, some unknown function, which is non-linearly related by some unknown way to your input. So here what we've tried to do is map this sine wave onto a saw wave, a square wave, and a sine squared. Now, what you see quite a lot in the field of reservoir computation is they'll show you some quite amazing looking predictions. But what they don't show you is what would happen if you did the same offline processing and weight optimization straight on your input data set, right? So, if you're doing reservoir speech recognition, you can have your snippet of voice. You put it through your reservoir and you train on outputs, but what tends to not be shown is what would happen if you ran the same recognition code on that raw piece of data. And when we first started, we weren't doing that either, and we were quite, very pleased with ourselves, how good this looked. But then when we started running the linear regression on the raw data, that also looked really good. So I think it's really key with these type of things that you're showing both yourself and the field what is your reservoir adding. So what we have here in blue is the same exact offline processing being performed on the raw IFT dataset, bypassing the reservoir. So the target here is in red, and you can see that the prediction performed on the FMR output is doing a good job of mapping onto that. Whereas when we're running that same linear regression approach on the raw data set, it's entirely unable to do this nonlinear transformation. And that's, the bigger the higher order the transform, the more apparent that failure is, unless you're running something through the reservoir. So we can really see here the benefit of putting things through our strongly interacting nanomagnetic system. So we took a different IFT, we took an inverse saw, and again, you get the same behavior. So here we were mapping onto a sine, square, and an inverse saw squared. And you can see that the black curve, which is the output of our reservoir, has done a good job of mapping onto that. Whereas running the same prediction code without the reservoir, it really struggles, and it can't adapt its curvature. So we also wanted to run a test, which was done in a nice memristor-based paper by Du et al. In 2017 Nature Comms. So what they've done here is they haven't just done a nonlinear transformation that cares about the current time step. We're also testing the memory capacity of our reservoir. They've looked at the prior, the t-1, and also two steps.
You should think of wrapping up soon, yeah.
Last couple of slides. And again, so even when we're looking at the hysteretic behavior, we're able to map on well, whereas without the reservoir, it still fails. So as well as transformation, we're looking at future prediction. So we take the chaotic Mackie glass waveform, it's commonly used in reservoir benchmarking. When we're looking at t+1, it looks like both the ASVI and the Raw input bypassing reservoir looks good. However, if you look closely, there's a common problem in prediction that's going on here when you're bypassing a reservoir, that it's simply reproducing the target data set, but one time step lagged. So it works quite well for a T+1. As you go more to a real world case in the future, T+10, where you're actually having to do some proper prediction, it totally fails if you don't include the reservoir. Now, something I didn't mention that's important here is where I was talking about wanting to embed this in devices and really reduce energy. In a real world use case, we've specifically chosen really short training sets here, just 100 steps. It's a lot shorter than is commonly used, but we wanted to have something where you might have a sensor that's having to spend energy on data capture, and so you're doing your best with really limited data sets. One more thing, we wanted to show the noise tolerance of our system. So what we've done here is taken the same sine wave input system, but we've injected white noise on top of that, and we're trying to do the future prediction 10 steps in the future. So again, you can see that without the reservoir, the prediction has totally failed. If you don't include the noise, the raw inputs are able to do this really well. But once you add noise, and especially the more noise you add, the more adding our reservoir adds to the value of the system. So wrapping up, we designed and tested a new artificial spin system. We engineered it so that you can move between the textures, and that enabled a whole bunch of nice things. So big changes in the spin wave spectra with nice impact from reconfigurable magnonics, specifically the analog style control, as you can tune the peak amplitudes. Also the big 3.8 gigahertz shift between the Vortex and macrospin modes. We showed that you can write in vortices, so linking this spin by spin microstate control to the large, more stochastic global field-based control methods. And then we've leveraged that synergistic package of behaviors into a new reservoir computation scheme. So in the future, we'd like to use the tip writing to seed certain prediction behaviors. So somewhere between full random reservoir and programmable neural network. We also want to put down multiple FMR pickups so we can have more inputs to feed our system. And I want to make a few thanks. So one, especially to Professor Karen Evershaw-Sitter and her student Jake Love for a really nice chat we had after their talk on reservoir implementations, which helped us a lot. And then once again, to thank all my co-authors and collaborators, particularly Killian Stenning for the design and implementation of the reservoir scheme, Alex Vanstone for establishing the FMR readout of the different microstates, and Troy for really great simulations tying together our microstates and spin wave modes and profiles. Thank you very much for your time.
Okay, thank you very much, Jack. So maybe we can ask some questions here. Let me actually talk about the double here. Let me allow to talk to Karen. I think you're on. Yeah, go ahead and ask your question.
So thank you very much for the talk. You've talked about the role that is actually done by the reservoir versus the pre-processing. And you've shown results where one of them was working and the other one was not working, where you really needed the reservoir. But can you quantify which role the reservoir has played?
So that's a good question. And if I go back a few slides. So to the best of our understanding, what the reservoir is doing is adding in non-linearities, which you can view as a type of harmonic generation, if you like. So you're creating these higher order terms, which are then present in the data set, if you like, for free. There's obviously some energy cost to run your thing through the physical reservoir, but that is adding in these extra terms that you're then, so we're not actually pre-processing at all, but the post-processing, your offline linear regression training, that linear regression training is able to then find these higher order terms in the data and use them to make a much better prediction transformation, whatever the task is at hand. So that's the best of our understanding. We're still diving into it, and we're really intrigued actually by the recent preprint that yourself and Jake just put up. So we want to run some of those task agnostic tests.
Thank you for your answer.
Okay. Mikhail, can you maybe unmute yourself and ask your question?
Thanks, Jack. This is a very interesting talk. And I'm just wondering about, say, technicalities of your reservoir system. How much time does it take actually to run 1 sequence? So how much time does it take to run this hysteresis loops in total, real time, I mean? And
it's a really good question. So at the moment, and you may have noticed I didn't mention it. So we're running this thing on a superconducting magnet. It's done in a PPMS. So it's, you know, it's by far from the ideal system. It's designed to go up to massive magnetic fields. We're using somewhere between 10 and 20 millitesla. So at the moment, we're transitioning, in the middle of transitioning onto an electromagnetic based system where you should be able to get up to kind of kilohertz looping. But at the moment, the looping's really slow because we're doing superconducting charging and discharging, just because that's what our FMR probe happens to be compatible with. So at the moment, you're looking at, for 100 of these data points, it could be as long as 12 hours. But, you know, really, this is a lab-based system. And the only reason it's taking that long is because the magnet is just the wrong one. So basically kilohertz range of, okay, thank you. It's as fast as you can sweep a magnet between, you know, 10 or 20 millitesla. So yeah, kilohertz, or even faster if you can get a big cooled one. Okay, thanks.
Okay, Jake, go ahead and ask your question.
Hi, Jack. Thank you for the really nice talk. So for more complex tasks than what you've shown here, data sets can often have patterns that occur over multiple timescales. And what's nice about your system is that you have shown that you can get different decay constants based on the number of training loops. Do you think there's a way to use the reservoir such that different regions have different decay constants, so Definitely, that your memory for system can capture patterns over a large range of timescales?
100%. Yeah, that's a really astute comment. Thank you for that. And that's one of the directions we're going to go in. So you can tune that based on a number of things. And one of the nice things about it being a bit-style nanopattern system, so you have these discrete islands, is the size and also the vertex spacing of those can control this. So what we're thinking is a type of chip you would have separate arrays with these different parameters. Each one can be relatively small, and you would be feeding your system optional weights from a few of them, which you'd then be able to train on and only keep the good ones. And we've already shown here that you really don't need too long training sequences. So that's something that we've got under fabrication at the moment, and we're excited to look at the results of soon.
Cool. So you can easily change this decay constant just by changing the sizes of the things as well?
Exactly. So for instance, some of the, where are we? If I try and show here. So where I've shown these kind of sequences of like how long it takes for the system to saturate, we can have it saturate. So by changing the dimensions, we can have it hit this point in anywhere between 300 and 5 or 10 loops. So we have a lot of control over that.
Cool, thank you.
Cheers.
Okay. Is there any further questions from the audience or Q&A? I don't see any moment. So with that, I think I'd like to thank you for a nice talk on a new way of doing reservoir computing, and a realistic one, seeing exciting new directions on this thing. And just a reminder to the audience that next week, due to the overlap with another workshop going on, we will not have a talk. And we'll continue the week after, as is in the schedule, with Macroscast. Okay. And with that, thank you very much, everybody. I'll stop here now. The streaming online. One quick moment.
Thank you very much.
Is ended. And yeah.